Yep.
I did part B?
Yeah.
I don't know which one they want to do. So here we go. Number 20. Solution. Here we go. To homework. (16). Solution to homework 16. Okay. So we have a brass sleeve with diameter equals what? 2.19620 centimeter. We have a shaft that's a little bit bigger. Steel, made out of steel, with diameter equals 2.19888. And in part A is you want to heat this to expand it, so to make sure this one fits through it. I want to expand that. Well, I need to expand this such that the D final, I want it to be at least equal to this one. A hair bigger, actually, but I want to be at least that one, or just a hair bigger. My D initial is 2.19620 centimeters. The change in the diameter is going to be D final minus the D initial. 2.19888 minus 2.19620, 0.00268. Well, I know the change in diameter equals alpha times L0 times change in temperature. 0.00268. Now I'm actually heating the brass. I have to look for alpha for the brass here. Where'd you go? Specific heat for brass, where are you? Gold, silver, copper, steel. Oh, what is it? I'm looking at the wrong table. Brass. Brass is 19 times 10 to the negative 6. Original one, L0, then 2.19620 times the change in temperature. So the change in temperature is 64.22 degrees Kelvin, which is the change in temperature still 64.22 degrees Celsius. The change doesn't really change. So the change in temperature is the final temperature minus the initial temperature. 64.22 equals T final. Initial temperature was 1220. So let's add 1220 to it. 76.4. Two significant digits, 76 degrees Celsius is your final temperature. So if you heat the brass to 76 degrees, it should be just big enough. Part B of the problem is working the problem backwards. So you know what? I don't want to touch the brass. I want to shrink the steel, cool it. So to shrink, excuse me, to shrink the steel, this is the steel here. The initial value is 2.19888. I'm going to reduce that to be what? 2.19620 centimeters. I'm going to shrink it to make it fit over this. This is brass here. That's the sleeve, and that's the steel. So the change in the length, or the change in diameter, is going to be D final minus D initial, which will be a negative value. Alpha for steel is different than for brass, is 12 times 10 to the negative 6 from the chart. The change in L equals alpha L0, change in temperature in Kelvin. Negative 0.00268 equals alpha, which is 12 times 10 to the negative 6. L0, which is what? That's D0. And delta T, the change in temperature, is negative 101.57. Change in temperature is what? T final minus T initial. 101.57. T final, the initial temperature was 1220. T final has to be what? Negative 89.4. Two significant digits, T finals negative 89 degrees Celsius. So let's try that answer. Yep. So just knowing which one they want to do, the sleeve or whatever, the shaft, you can either expand this by heating it, or you can shrink this by cooling it, and it will fit. This actually, if you see a plumber come to your house trying to loosen, like when they want to join two copper, they have this shelf, this ring that goes around them, they heat that, then they both slip over it, then they let it cool down. The ring itself is really thin, it holds tight there and nothing leaks now. So that's number 20. Notice if I did this with area, not much of a difference, because I can look at the area instead of the length. And I did this with area, and this is what it looks like if I look at change in area. More math, but look at the temperature, still negative 89. Because you want that area to shrink, not just the length, the diameter. When the diameter shrinks, so does the area. So if you use the area or the length, it really doesn't matter. The volume, that's not an issue. How long that piece, we don't care how long it is. We don't care if the length shrinks or not, because there's even nothing mentioned about the height of it. So as long as this section is small enough to fit inside that. So I shrunk the steel here to negative 89 degrees. If I go at negative 89, it will fit actually inside that. I'll put that with the notes. $16.33. God, I hate this coughing. They're not in any order, huh? Oh. I'll go back to it because they're not in order. 33. Okay. And so let's assume that 67.3 joules, that's energy, Q. Heat is added, so this is equal to Q, is added to a 122 grams aluminum at 22 degrees Celsius. What is the final temperature? What is the final temperature? Then I go back at 2 o'clock for an appointment. Okay. Well, let's look at the heat. Q equals what? C times M times delta T. And we're talking about aluminum, I think it's 900, the specific heat for aluminum. 900, so 67.3 equals C for aluminum is 900, the mass is 0.122 times the change in temperature. 900 times 0.122 is 10. I can't be. Yeah, well, it is 109.8. What's the change in temperature? 670.3 divided by 109.613 degrees Celsius. So the change in temperature equals T final minus T initial. Change in temperature 0.613 equals T final, which is I'm looking for, minus the initial, which is 22 degrees. T final has to be 22.613 degrees Celsius, or Fahrenheit. Or that, I'm sorry, Celsius, because that was Celsius here. Yeah. And it doesn't say how many significant digits to use, so I'll assume 3. 22.6 degrees Celsius is the final temperature. Yep. Let's look at 39. Oh, 36, I'm sorry. Okay. We have a bullet. That's supposed to be a bullet. I don't know why the bullet looks like this. There we go. We have a 5 gram bullet made out of lead. Is fired into a fence post. This is the post of fence. I don't know if it's wood or what. Doesn't say anything yet. The initial speed of the bullet, V initial, is 230 meters per second. When it comes to rest, half of the kinetic energy goes into heating the bullet. Half of it, as it goes through that wood, wood, aluminum, whatever post here, half of that was going into heating that. So if you grab that bullet with your hand, probably going to burn you. Half of the kinetic energy went to heat the bullet. Half of it. Well, what's the kinetic energy of that bullet? It's 1/2 the mass times the velocity squared. 1/2 the mass of the bullet, which is 0.005, you have to convert to kilogram, times the velocity squared, which is 230 squared. .5 times 0.005 times 230 squared. 132.25 joules. Half of that number, it was heat. That's what Q is. Half of that number went to heat the bullet. So divided by 2, 66.125 joules. It heated the bullet. Probably now, how much does the bullet temperature increase by? That's the change in temperature. Q equals C times M times delta T. 66.125 equals, now C for lead. Let's look at the chart on page 529. Specific heat for lead, 128. Times the mass, which is 0.005, times the change in temperature. Can we get the change in temperature? Well, the temperature increased by 103.3 degrees. Using 2 significant digits, that's what? 1.0 times 10 to the second, or 100. The temperature increased by 100 degrees of that bullet. Notice when you rub your hand, you feel that heat. As the bullet goes through that wood, assuming it's wood there, it's rubbing against the wood and it's getting hotter and hotter. That's why the temperature increased by 100 degrees. Number 39. $38, $40, up $39 right there. Okay, this is backward here. It says 2,600 joules, that's the amount of heat, Q, was added to 190 gram object. They're not telling us what the object is made out of. But the temperature increased. There's a change in temperature of 14 degrees Celsius. That's the change. What is the heat capacity? Find C. Again, the same equation. Q equals C times M times delta T, or M times C times delta T. C is unknown, 0.190 the mass, temperature is 14. I'm getting C to be 977, almost aluminum. Aluminum is 900. Using two significant digits, that's what? 980? $2,600 joules added to one. Okay, let me just double my math. 2,600. 190 gram, I think 190 gram, divided by 0.19, divided by 14, 977. Express your answer using two significant figures. 980. Why does it tell me I'm wrong here? 2,600 joules added to 190 gram object. I give up. $190 says. What'd you get for a number?
I got mine wrong. I did the same thing that you did, but with my numbers.
If 2,600 added heat are added to 190 gram object, its temperature increased by 14 degrees. There's no way, unless that's supposed to be 260. Just curious if that's 260 instead of 2,600. That was a typo. 260 divided by 0.19 divided by 14. Nope. 2,600 added to I have no idea. Oh, 980. Yep. I don't know how they come up with that number. What is that? Specific. Oh, wait a minute. It is 980. Yeah, it's 980. You know what? I know why. For part B here, what's part A? For part B, it says what is the specific heat? That's small c. That's 980. But if you put 980, you get it wrong. You know why? They want it in kilojoules. So in kilojoules, that's what? There will be 0.98 K. They want it in kilo. I didn't see the kilo. Did it say kilo next to it? Yep, K joules.
That's for part A?
Yeah, PB, I mean. Small c. We're looking for small c. Part A, I think, what are they looking for? Capital C?
Yeah.
In kilojoules per second. Well, if you look for part A, Q equals capital C times delta T. Q is what? 2600. This is part A. I didn't see the capital here. Capital C times the 14. $185, and they want 2.7, two significant digits, that's 190. But they want it in K. It looks like in K that should be what? 0.19 kilojoule per temperature, per degree Celsius. This is small c per kilogram. Is it correct?
Yeah.
Yep. But be careful, they want kilo. Kilojoules per kilogram degree Celsius. Small c, that's when you include the mass per kilogram. Capital C is without the mass. Q equals C times delta T. So you have to be careful. Are they looking for A, are they looking for B? Are they looking for capital C or small c? And the part I missed is the K at the end. They want in kilojoules. I didn't see it. It's right there looking at me, but I just didn't spot it. So 0.98 or 980 for C, which is 0.98. This is 190, which is 0.19. Sometimes I'm blind. It's not really seeing them, it just, my mind doesn't even notice them there. If I saw them, I would have looked at them. And the last one, 1680. A 206 kilogram rock sits in full sunlight on the edge of a cliff. So here's the cliff, probably down here. There's the rock. That rock has a, oh, it's a big rock, has a mass equals 206 kilogram. So the temperature of the rock is whatever the temperature outside that day there. The height here is 4.90 meters. The temperature of the rock is 30.6. If the rock falls from the cliff into a pool containing, here's the pool here, it has a volume 6.80 cubic meters of water. Temperature of the water of the pool is 15 degrees Celsius. That rock is hotter than this, going to warm it. Assume the specific heat for the rock, C for the rock, is 1010. The pool, I'm assuming, is clean water, not salty water. The C for the pool is 1000. And the question, what's the final temperature of the pool? Here's the part we have to realize, actually. There's a reason why they gave us the height of the pool. It's not you just took the rock and put it in. There's that water, that rock, when it comes down, when it hits that water, what's going to happen? It's going to go through that water. It has kinetic energy. As it goes through the water, it's pushing the water away. Just like your hand, when you're rubbing your hand, what happens? You get that heat. As the rock goes into the water, it's pushing the water away, just like that bullet you saw that, it's actually heating that water from the friction. So let's see. I'm going to assume all that kinetic energy is being sent from the rock into the water. So when the pool actually, the rock is sitting up here, it has potential energy on the top. So let me just look at the rock first. This is here. Let's look at the potential energy at the top and the kinetic energy at the top. Down here at the bottom, let's look at the potential energy and the kinetic energy at the bottom. Okay, potential energy at the top is the mass, which is 206 times gravity, which is what? 9.8 times the height, which is 4.90. They gave us the height for a reason. The kinetic energy is really zero. The rock wasn't moving. The sum of the energy at the top, the sum of it, is 9892.12. The bottom here, potential energy, if I use the water as reference here, the beginning of the pool here, potential energy is 0. Kinetic energy, it's 1/2 mv squared. You get the velocity of that. Let's say kinetic energy. I don't care about the velocity. It has 0 potential energy or kinetic. So that kinetic energy has to equal to 9892.12, just like that bullet that went through that fence there, the post. And that's what that number is equal to. Now, we need to look at the water here and the rock. Well, before we get to the water, we're going to need the mass of the water. So in case you forgot, mass of the water, the pool, the water in the pool, it's equal what? Rho times the volume of the pool. Rho for water is 1,000. I'm sorry, specific heat for water is not 1,000. Rho is actually 1,000. 4,186, right? Rho for water, the density is 1,000. Rho, which is 1,000, times the volume, which is what? 6.80. That's 6,800 kilogram. That's how much water in that pool. The rock is going to fall. This has more heat. It's going to sit in the pool for a while. It has kinetic energy of that much. All that, if you let it sit for a while, the net result will balance each other out. The temperature will rise. We have no change in temperature, and we have a thermal equilibrium. Which means what? If I take the amount of heat that's gained plus the amount of heat that's lost, plus the amount of heat that I'm adding for the rock coming down, which is 9,892.12, should equal to 0. You got to take all this energy, you adding that to the pool. From going through that water, it's going to heat the water. It's going to add heat. That's a positive value, not a negative. The friction. Let's go through the math and see who gained heat. Well, the water in the pool. And it's the mass of the water, C of the water times the change in temperature. Who lost heat? The rock. The mass of the rock, C of the rock, change in temperature for the rock, plus the 9,892.12 is equal to 0. Ready for big numbers? Here we go. The mass of the water, 6,800 times C for water, 4,186, I think. Let me just double check that. 4,186 times the change in temperature, which is final minus the initial. What was the question? What is the final temperature? Where does the question go? I closed, I guess. Number 80, was it?
Yeah.
What's the final temperature? Yep. So T final minus T initial. What was the initial temperature of the water? 15? Mass of the rock. The rock is what? 206. C of the rock, it says assume it's 1010. Final minus initial. The initial of the rock was what? 30.6. Plus 9892 equals 0. I'm dropping the 0.12. $6,800 times 4,186. Ready for these numbers? 2,846,4800 minus 4,269,7200 plus 206 times 1010 equals 20860T minus 636636 plus 9892 equals 0. Let me take the T's, put them together. Add all the numbers together and see what that number is. I think that number should have been a minus. Right? Then negative 9.8. That should have been a minus. Why minus?
The rock's falling.
Yeah, didn't we lose that heat? Friction? We lost it to the water? Not a plus. The rock lost that. So let's look at these numbers. 2.8, 4.6, 4.8, 0.0. Better double check your numbers, plus, because 2.0, 8.0, 6.0. If I push all the right button, I have 2.8, 6.7, 2.860T. If I take all these minuses and add them and move them to the right side, they become a plus. Let's see, 4, 2, 6, 9, 7, 2, 0, 0, 0. Add to it, 6, 3, 6, 6, 6, 3, 6. Add to it, 9, 8, 9, 2 equals. I hope I got all the numbers. To solve for the temperature here, final temperature, we divide by 2, 8, 6, 7, 2, 8, 6, 0. It's 15.11 degrees Celsius. Big deal. The temperature went up by 1 degree, 0.1. Let's see if that's correct. All the numbers are 3 significant digits, so 15.1. Correct. T final equals 15.1 degrees Celsius. So that's a minus because we're losing that heat. The rock is losing it to the water. That's why it's a minus, not a plus. Due to friction. We lost that kinetic energy too. Here's probably where you can catch your mistake. If you made that a plus, probably your number will be more than, below 14, below 15. How can it get colder when you put something warmer in the pool? I don't think it will be below 14, actually. Below 15, to be honest with you, it won't be, because that's not too much. We're done with the thousands compared to that number. That's just a puny. So even if you didn't count that, you probably end up with that answer once you round your answer, just by luck. But you have to include that really in it.